All right, welcome to the lesson 2.5, proving statements about segments and angles, geometry notes. So here we go. Big goal here for today is kind of to extend concepts from previous lessons. If you recall, 2.4 talked about algebraic, really proofs and justifying steps in an algebra situation. We previewed kind of where we were going we finished with a geometry proof example. Here we really get into almost exclusively working with geometric concepts and kind of introduce how to do a full formal geometric proof. So here we go. Let's jump in. Let's get it going. Little bit of notes, just at first, actually a little bit of a recall. So we defined earlier in the school year the definition of we defined what it meant to be congruent. So for the most part, I think if we think about congruency as same size, same shape, whether we're referring to angles or segments, same size, same shape. That's what congruent means. They have the same size and shape physically. Attached right with that is equality. What's the difference? We kind of did notes on congruence versus equality, and they go hand in hand, but they're not interchangeable. They're not identical. This is when we're talking about angles A and B being congruent, we're talking about the physical angles, I've said it now for the fourth time, being the same size and shape. Because they're the same size and shape, their measures, the actual degree measure, 30 degrees is equal to 30 degrees. So measures, remember, is talking numbers, values, whereas the congruence is talking about the physical objects themselves. Okay, like I said, totally related. They go hand in hand. You can't really have one without the other. How could two segments have the exact same length, but then not be the same size and shape? So they are connected. If you have one, you have the other. And where we're going to use is why we're reviewing it now, because we're going to convert. Sometimes we'll have information presented as congruence, and a lot of times we'll want to work with equality. So we just say, you know what? Angle A and B are congruent. Okay. By the definition of congruence, those angles have to have the same measure. So you can kind of see, put a pin in that. We'll come back and see wait, okay, what does that mean? Why would we want to convert this to this, or vice versa? Why would we want to convert equality to congruence? So we'll use the definition of congruence, kind of long story short there, as a converter to go between congruence and equality. Okay? All right. Next thing. When we're talking about, it's come up a few times, the word proof. Obviously, that's show me some proof. That's a word that has different meaning in different settings. For us, it's actually like a thing we're going to do. We're going to do a proof. A proof is a kind of a very logical step-by-step argument showing a statement is true. So it's slightly different meaning than maybe, instead of looking for some proof, finding evidence. A proof is a formal kind of outline of showing a statement is true. Okay. We'll exclusively work with what's called a two-column proof. So a two-column proof, again, if you saw the previous lesson, this should say 2.5 up here. Oh, Mr. Kroll. Anyways, a two-column proof, it has a numbered statements. Okay, and then everything on the left, are your statements, and on the right is your reasons as to why that has to be true. Let's look at, kind of how that's set up. So left-hand column, same thing here, two-column proof. Left-hand side is your given information, freebie information, and then everything else that follows is the result of applying some known property or fact to these statements that are already in the proof. We might introduce stuff, but again, we have to introduce it using what we would use is definitions, postulates, theorems, and some of those algebra properties. So left hand is the statements, right hand is your reasons, your justifications, your explanations as to why something on the left has to be true. Okay? So really, that's kind of the notes. We'll do a little bit more here, kind of mid-lesson, break it up. But for the most part, it's okay. Let's look at what does it mean to formally prove stuff. That's kind of the best way to get them figured out is just to do some. So this is actually just to kind of look at. We did this as I pulled up and kind of put it in, typed it up as far as our last example from the previous lesson, where we kind of just took a quick look at, where are we going? So this is what it looks like. We're just recalling that basically we had some angle measures that were equal, and the goal was to prove this, that DBA was congruent to EBC. And there's a very formal process, so it lays out where the given information, that's how you kind of start your proof. The angle addition postulate came up. We did ours slightly different order if you're remembering back to our 2.4 notes. We did our angle addition postulates right away. There's a substitution property of equality, and then we connected everything using the transitive property. That's a pretty typical kind of layout where you start with maybe some given information. You would potentially introduce some information into the proof using, an angle addition or segment addition postulate. And then really the last couple steps are usually connecting, and that's kind of what we did. We connected information using substitution. We connected information using the transitive property. So that's a general outline. I'm not saying every proof goes that way. So this one, not really a whole lot to do other than just to kind of recall, oh yeah, that's right, we did something like that. Let's do one here. This is a kind of a hybrid one where it's a geometric, but still using some of those algebra concepts. So let's get in, take a look. 6 steps are shown, complete the proof basically. All right, so here we go. We got a picture, STU, segment ST, segment TU, big segment SU. What are we given? We're given that T is the midpoint of SU. Okay, that's good information to have. That's definitely given information. This is one, and it doesn't happen often, but there will definitely be a proof or two that there's more given information than just this. Like that's a free piece of information. T is the midpoint of SU. We need that. That's very helpful. We're going to have to use that information. But there should be other stuff that we should add, and this isn't a great look because there should be a blank here on step 1 where we say what else is given to us. We're given some segment lengths. Okay, that's not something we're creating. That's not something we're making up. That's free information. We know. So I'm going to add that to my givens here. That the length of ST is equal to 7x, and on top of that, the length of TU is equal to 3x plus 20. So remember, I'm using my symbols correctly. I don't have a bar above the TU here. I don't have a bar above the ST because we're talking about the lengths themselves. The length of TU is 3x plus 20. The length of ST, again, that was given information. All right, let's follow here. The approach really has to be with the proof. I can't jump to like step 4 and try to just plug in, okay, what am I doing here? I really always kind of have to take this top-down approach. All right, so we get the given information kind of formally entered into the proof. We write it down. And then here's my compass. I'm always trying to guide myself using the proof statement. So I look there and I say, okay, x equals 5. I see some x's in here, x and x, but they're 2 separate equations. I think at some point we're going to have to get these into a single equation because we know this proof has got to finish with x equals 5. All right. So I'd encourage you to kind of do the same thing. I know these ones are filled in for us, but we kind of got to, let's see how we're working our way to that point. So let's see what the next thing that happened. So, whoever did this proof said, all right, the next thing I want to state is that segment ST, so the physical segment ST, is congruent to physical segment TU. All right, that's what that's saying. I went through and just marked it. You could see I marked them as congruent. I used 2 tick marks to show that they were congruent. And the reason, I always need a reason to, how did you know that was true? Well, there was a piece of given information that said T is the midpoint. Oh, okay, I know what the definition of a midpoint is. It says it's in the middle of a segment. It divides a segment into 2 congruent segments. There we go. That's how that came about. We decided we wanted to talk about ST and TU. So I said, hey, definition of a midpoint says that has to be true. This is what we had talked about earlier in the notes, that what happened from step 2 to step 3. Well, the bars disappeared, right? The little bars above the top disappeared, and this little congruent, the little squiggle disappeared. So now we're talking about the actual length of segment ST is equal to TU. There it is. There's our definition of congruence. We converted from congruence to equality. All right. And again, that's a pretty typical, not always, but a lot of times we want to get out of congruence because with equality, and you can kind of see on the proof statement, I always said, always look back here. This is equals, right? It's not x is congruent to 5. So I kind of want to get out of congruence and get in equality mode. And that'll allow us to maybe do some substitution. Notice in our other given information that we added, we said ST equals 7x, TU equals 3x plus 20. So now we're talking about things that are all in equality. Equality, equality, equality. All right, next line. So now we actually have a little bit of work to do here. So where is this statement coming from? That 7x equals 3x plus 20. I think a lot of people maybe look at it and say from the get-go, like, what? I knew that this was the same. 7x equals 3x plus 20 because it was a midpoint, because those were congruent, right? So that's kind of how we get to this step. What actually happened? We basically took, and again, you would leave your proof normally, but I want to make sure you kind of see what's going on. We know that ST, this ST right here is equal to 7x. I see another ST right there. So what we can do is we can say, get out of here, ST. I don't like you. I'm going to replace you with something that I know you're equal to. So that's where that 7x showed up. We substituted the ST out and replaced it with something it was equal to. Similarly, we said, hey, TU, I don't like you. I want to replace you with something that you're equal to. You are equal to 3x plus 20, so I replaced you with that. So we took the previous statement. So if you notice, everything has kind of gone from here to here. So we took step 3. How did we get from step 3 to step 4? We substituted substitution. Property of equality says you can replace things that have equal values. Okay. So from step 4 to step 5. At this point, so I always said I got to do a better job of referring back. Every step, I'm going to look and say, are we here yet? It's like the old road trip. Are we there yet? Are we there yet? Are we there yet? No, we're not quite there. I think we're getting closer. We're down to an actual equation. It started with words. We're down to an actual equation right now with some x's, some numbers. We want to finish this with x on the left side and just a single 5 on the right side. So here's where I said earlier, it's kind of like a hybrid now. Now we're going back to the 2.4 stuff where we're using algebraic properties to kind of get this just down to x equals 5. So we should be showing work somewhere. This is one I'm probably just going to roll through it here. It's telling us we use the subtraction property of equality. What got subtracted? I'm thinking we're going to have to combine these like terms right here, 7x and 3x. So I'm going to have to subtract a 3x from both sides. So that's going to leave us a 4x on the left side and a 20 on the right side. We've applied the subtraction property of equality. So we went from step 4 to step 5. And then finally, I think just about everybody says, oh, yeah, I know how to solve that. Divide both sides by 4. And that's exactly what we would do. We would divide and say x equals 5, division property of equality. And that's that. Okay, so a little bit of a new look there for us. This one had a lot done for us. We'll eventually get to a spot where that's blank, and we're filling that whole thing in. We'll do that'll be our last one we do today, a blank one, but that's the idea. A little bit of an algebra, a little bit of a geometry proof. All right, let's look at a different one. I would say this one's more true geometric, where it's only a 3-step proof. There's definitely some stuff that we're going to have to fill in, but there's also some freebie stuff, right? We said, how do we start every proof? It always starts with the given information. So I look at this and I see that BC, I haven't even looked at the picture yet. I'm just kind of jotting this down, but I am going to look at the picture just to kind of see what's going on. BC, it tells me it's marked. So BC is the exact same length as AB. If it wasn't marked, I just kind of re-highlighted it. Whoops, given. That was given information. And still, I'm gonna, I have the ability to do it, and you would too, right? Obviously, you could use a piece of paper and kind of cover up what's going on there. So after I get my given, I look at my picture, I see what's going on. AB is the same length as BC. Okay, I got that. Here's my compass, our roadmap. We got to get to this point. We want to say that AC is equal to AB plus AB. Is that true? Of course it is. AC is length of AB plus AB, but that's not what the picture looks like. We got to kind of modify what's going on here. So I'll use this word a lot. We need to introduce AC into the proof, because right now, with the way it's covered up, all I see is BC and I see AB in the proof right now. There's nothing mentioned about AC. So we know, because the proof statement says something about AC, it's got to get into the proof. So I think step 2 is a good time to introduce AC to the proof. We already have AB in there. That's a good thing. So there's a couple ABs right here. We at least have it in right now. I need to be able to say something about AC. So for right now, one of the best ways that we're going to use to introduce things into a proof is the segment addition postulate. It's laid out here for us, the segment addition postulate. So we do have to go back and kind of recall. I'm not saying there's not like you have to tell me word for word what the segment addition postulate says, but we have to understand how it works. The segment addition postulate says the length of a big segment, so segment AC, that length is equal to the length of this small segment AB, and I'm not using bars above the tops because these represent lengths, and that's equal to the length of AB plus the length of BC, whatever those lengths are. So that's a very, very generic blanket statement, right? We don't know numbers. We don't know anything really other than if I take the length of AB and I add it to the length of BC, it has to equal the length of AC. That's a property that our postulate we talked about earlier. We say, yeah, of course that has to be true. How could that not be true? And that would be true. But what did that do for us? Like, what's the big picture here? Look what we just stated in step 2. We stated AC. Okay, well, holy cow, that starting to look like my proof statement is equal to the length of AB plus. Oh no, darn it, we're not quite there yet. This one, the proof statement says AB. What we just wrote says BC. So now I think we've introduced everything we needed. AC is in the proof. AB is in the proof, a couple different spots. The only thing we have to do is maybe connect these two statements. So just like the last one, how can I connect step 1 and step 2? So our lower left, our step 3 here is always going to end up being our last statement is always going to be your proof statement. So there we go. We know that's where we ended up. How did I get there? Just like before, we said, you know what? This is so close. I'm going to replace this BC with something that BC is equal to. BC is equal to AB. We were given that information. I'm going to replace it. I'm going to substitute it out. Substitution. I'm going to replace it with something that it's equal to. What allows me to do that? The substitution property of equality says you can replace things that have equal value. So that's what we did. All right. So we're starting to build, obviously that's two very different proofs, one involving a segment, some algebra, one involving more just the segment addition postulate. Well, I guess they both have the segment addition postulate going on, but the approach is what stays the same. Start at the top, work your way down using this as your guide. All right, let's do one more. I think this next one has quite a bit going on. It's got some angles. We'll do that, and then we'll add a few more things to the notebook, okay? So holy cow, when I look at this all like, wow, blank, so what's going on here? Let's help ourselves out, not overwhelm ourselves, and just say, all right, here we go. Where do I start? I know how to start a proof. I'm going to get my half point by getting the given information. We'll look at the picture in a second. The measure of angle 2 equals the measure of angle 3. All right, let's take a look. Where is that? Okay, that's marked for us. 2 is congruent to 3, or they're marked as congruent, but we know their measures are equal. And we also know that the measure of angle AXD is equal to the measure of angle AXC. Awesome. That's free information. That's given. That one's kind of hard to mark on the picture. So I'll use the colors maybe to help me. AXD is this angle, and what are we talking about? AXC is this angle right here. So I'm trying to highlight them both there. You've got the pink and the blue angle are both the same. They're made up of a red, 2 and 3, which we know are the same. What we're trying to show is, does 1 and 4 have to have the same measure? And I think, yeah, of course, like that's the one we would say. It's kind of like the flashlight one that we did in the previous lesson, or that we looked at earlier today, that how could they not? The pink angle is made up of 1 and 2. The blue angle is made up of 3 and 4. We already know that 2 and 3 are the same. We know that the big angles themselves are the same. So there's no way that 1 and 4 could not be the same. So it's like we talked through it. Isn't that enough? No, we got to formally go through and do it. Okay. So let's take a look. We're taking that top-down approach. I look at this proof statement and say, all right, at some point, angles 1 and 4 have to be spoken about, have to be introduced into the proof. Right now, nothing has been said about angles 1 and 2. Let's take a look. Oh, it's showing up just like that. So the measure of angle, let's see what this says here. The measure of angle 1 plus the measure of angle 2 equals the measure of our pink angle AXD. Yeah, I buy that. Right? We kind of said that those are the two that are making it up. The measure of 1 plus the measure of 2 equals AXD. In the same breath, basically, the measure of angle 3 plus the measure of angle 4 make up the measure of angle AXC. Yeah, we said that. That's very generic. That's very just, yep, 3 plus 4 equals this big blue one. 1 plus 2 equals the big pink one. Extremely generic, just like the last two, except when we were working with segments, we used the segment addition postulate. Here we introduced material. We didn't use it in this one, but in the previous one, we used the angle addition postulate to introduce material. Guess what? We're introducing angles 1 and angle 4 into the proof using a generic statement. This is absolutely our angle addition postulate. So I'm abbreviating there, and you're more than welcome to use that same abbreviation. The angle addition postulate says that that has to be true. Add two small angles together to get a big angle. All right. So they're there. 1 and 4 are now in the proof. I don't think we have to reintroduce anything. We're talking equations. That's awesome. Everything's equation. That's where we want to be. I don't think I'm going to have to convert anything. It's just a matter now of let's connect these statements, maybe using some of this stuff up above here. So let's take a look. Where is this kind of leading us here? It's telling us we're going to use substitution. We have some options. So here's where it can kind of get tough. There actually is quite a bit of information in this proof. 2 equals 3, AXD equals AXC, 1 plus 2 equals AXD. So there's some overlap. There's AXD showing up a few places. AXC is showing up a few places. 2 and 3 are showing up in a few different places. Here's kind of my take on this one. I want to tie these two statements together. I want these in the same equation. So what I'm going to do, wherever I see an AXD, right, what do I know AXD is equal to? It's equal to this thing right here. So I'm going to replace, and again, don't necessarily go back through and cross this off. I want to be able to read your proof. But I'm going to replace this AXD in this statement with the measure of angle 1 plus the measure of angle 2. Okay, because I know that AXD is equal to 1 plus 2. We said that. So I'm replacing this AXD with 1 plus 2. I'm just kind of rewriting this statement right here. Very, very similarly, in that same statement, I've got an AXC on the right side. So I'm going to replace this AXC with something that I know the measure of AXC is equal to. It's equal to the measure of angle 3 plus the measure of angle 4. Okay, that's kind of tough because this is forcing us to do it that way. When it says substitution, it's kind of forcing us to do it that way. Whereas if this was totally blank, there's options as far as what do you want to substitute, when do you want to substitute. So that's where we're sitting right now. And I'm always looking back. I'm checking right now. All right, are we there yet? Are we there yet? Well, I think we're a lot closer. Now I'm down to a single equation where I've got the measure of angle 1 on the left. I've got the measure of angle 4 on the right side, so that's really good. There's just some extra stuff right now. There's a 2 and a 3 hanging out right there. So let's see, where are we going to go? From step 3 to step 4, what changed? One tiny little thing changed. The 1s are still there. The equals are still there. The 3s are still there. The plus 4 is still there. The only thing that changed was this 2 magically got turned into 3. Or was it magic? I don't think so. Go back to this statement right here. We know we were told originally that 2 and 3 were the same. 2 is equal to 3. So it's kind of that same idea. Wherever I see this 2, I'm going to say, get out of there, 2. I don't want you there. I don't like you there. I am going to replace you with a 3. How do we replace things? It's another example of using substitution. The substitution property of equality says we can do that. All right. We take a step back. We look. Are we there yet? No, but we are a heck of a lot closer. We've got this 3 on both sides. You know what? What would make this perfect? Just get rid of these 3s. Can I just use my eraser and say erase you? Not quite, but almost. Oh, maybe we did do that. Holy cow, the 3s disappeared. How do you get rid of something on both sides of an equation? We would have to subtract it. So we applied the subtraction property of equality to get rid of those 3s. All right, that's tough. That's the only way to kind of get through this is to keep following, using the examples, think about what's coming next, developing that process of always looking back here. But hopefully, even by now, if I look at these, I think 4 proofs we've done, 4 geometric proofs. In our class, we're keeping a running tally of how many we're using, but how many times has the angle or segment addition postulate come up? Let's count. 1, 2, didn't come up in this one. There's 3, 4, 5 if you count these as 2 separate ones. So those are the ways we're introducing material into proofs. How many times has substitution come up? Substitution. 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 Uh-oh. 2 more substitutions. So those have come up quite a bit. So within 4 proofs, they all seem different. They all feel pretty different. But there are some things that are pretty common that are showing up in a lot of them. Okay, some different stuff. We saw the definition of midpoint was kind of an exclusive one there, but that'll be one that we use. Transitive property came up in that first one. All right, so let's take a quick break here. Back to our notebook. Let's add these to our notebooks. Very similar to the previous lesson, we have 3 properties of congruence. The reflexive property of congruence, the symmetric property of congruence, the transitive property of congruence. Same exact names that we had with equality. We just have the properties as congruence. Okay, kind of like we talked about earlier with that definition of congruence. It'll kind of depend on how the information is presented to us. So yesterday, or in the previous lesson, we talked about, if something said the length of AB was equal to the length of AB, hey, that's the reflexive property of equality. Maybe that's how the information is being presented. It's being presented with equals, so we would want to use equality. But maybe there's an example where we're working with congruent segments. It might be in our best interest to save time and just effort to use a property of congruence. So that's the only thing that's going on right now is we're changing kind of format, the same 3 properties being applied the same ways. AB, all with congruence. So the symmetric is still our flipper. AB is congruent to CD. Flip it over. CD is congruent to AB. Transitive, that's our connector. AB connects to CD. CD connects to EF. Therefore, we can cut out that middle and just say AB is congruent to EF. Okay, same thing applying with angle. So add those to your notes. Still, right now, it's mostly just recognition. The one that might come up in a proof would be transitive, connecting information, but for example, 4 here, all I would be asking is just name what's being illustrated. Okay, so we're told that RST is congruent to MNP, MNP is congruent to RST. So what actually ended up happening? It flipped. That is our symmetric property of congruence, though. So just pay attention to your symbols. Second one, or part B, AB is congruent to FG. That same, so here we go, that AB is congruent to FG. That same FG is congruent to MN. If we cut off, or we kind of cut out that overlap, AB gets connected to MN. That is a definite example of our transitive property of congruence. Something saying is congruent to itself, that's very a typical, very straight up example of the reflexive property of congruence. Let's see, what are we getting? We got to have a repeat here. It looks like angle Q is congruent to angle V. V is congruent to Q. We flipped it. So that's just another example of our symmetric property of congruence. Okay, so I'll say it one more time. We're not really using these a ton in the proofs yet. We will. Reflexive will come up definitely in future, maybe more chapters, chapter 3, that we'll take a look at that. But transitive, we saw it, right? Transitive property of equality came up in that first proof. So that's one that potentially is going to use it to connect information. You can kind of see how it connects it, okay? All right. So last thing to finish with, let's look at a couple. It's not going to hurt to look at a few extra proofs. There's some different stuff, but again, if I just, before I do anything, I start to look, definition of congruence, definition of congruent angles, angle addition postulate. Holy cow, let's tally those up. There's another tick mark as far as using some of that information. And then we'll finish with, a blank one. We can do it. Let's start here though, okay? Same top-down approach. I'm trying to keep these, approach these always the same way. At this point, we definitely know how to start. It's a word for word. Just get it down there. But then we want to step back and look and see, what did we actually write? I'm talking. I'm not even really thinking about what I'm writing, which isn't a good thing. I'm just trying to get some of the mechanical stuff done. All right. That says ray BD. So let's look at the picture. Here's ray BD. bisects angle ABC. Okay, I think I know what bisects means. Bisects was a term that came up in chapter 1. It means to cut something in half. So this ray is cutting the big angle into half. I guess that means 1 and 2 have to be the same. Were we told that 1 and 2 were the same? No, that's something that I'm applying. That's something I'm using my knowledge of what bisects means to add those markings there. So I actually have to formally state that. I think it's something we'll do as we go down here. Let's take a look at that proof statement. We know at some point we want to get to equality. Right now I just have a sentence, like a word sentence. So I do have to convert from words to equality at some point. We need to talk about the measure of angle 1 at some point. That has not come up yet in our proof. And we'll see what we can do with this ABC. Is there a way I can get this from a word, from a sentence, to like an equation? So that's kind of what I'm thinking here we're going to have to do. Let's take a look. With these fill in the blank ones, like I said earlier, I'm not a biggest fan because it forces me to do them a certain way. Whereas if it's blank, you think, oh wow, blank, daunting, but you actually get some freedom, you get some flexibility on how you want to approach it. So let's see what we're saying here. It looks like we're introducing this 1 into the proof. 1's showing up right now. Angle 1 is congruent to angle 2. Now I already marked that. I already marked with arcs 1 congruent to 2. How did I know to do that? I got to think back. What told me that it was okay to put those markings on there? This one word right here. We said, oh yeah, I know what bisects means. It means to cut something in half. So I literally applied the definition. I'm using DFN for definition. The definition of bisects or bisect or angle bisector. So the definition of bisect told me that had to be true. Okay, that's a step in the right direction. That gets angle 1 into the proof. Now it's not quite there yet. This is the measure. So I think, this would be a good time, and here we go, that definition of congruent angles. Remember we said put a pin in that. It was one of the first things we talked about here in the proof was the definition of, the definition of congruent angles. If I said something's congruent, I know for a fact their measures have to be equal. How do I know that? Because the definition of congruence says that has to be true. So here we go. It's finally showing up in one of our proofs. The definition of congruence, the only thing that happens is we're going from these congruent symbols. I add my little measures. The measure of angle 1 has to be equal to the measure of angle 2. Why? Because the definition of congruence says so. It says if you have congruent angles, their measures have to be equal. We're getting better. I like this because now we're talking equals. That's a good thing. We've got measure of angle 1 is shown up in my proof. Let's work on this ABC here, I think, a little bit. Right now, it's like the physical segment or the physical angle ABC. We need to get down to the measure of ABC. So let's see what's going on here. I think that's the next thing to work on. Measure of angle 1 is probably in decent shape right now. Here we go. Is this the third or fourth time that this is showing up today? We must be introducing material. The angle addition postulate is our way right now that we know of to introduce stuff into a proof. So we said, let's introduce the measure of angle ABC. If we're going to introduce things, let's be strategic about it. Let's talk about the measure of angle ABC. So I look at my picture. I see big old angle ABC right here. And I say, what's comprising? What's making up that angle? Angles 1 and 2. So I'm going to write it like this. I'm going to say the measure of angle ABC, okay, because that's going to put my ABC on the left, is equal to, what is it equal to? Just looking at the picture, very generic. This is always a very generic statement, just using a picture. It says it's equal to the measure of angle 1 plus the measure of angle 2. That's just generic. I just looked at the picture. That's kind of coming out of nowhere. Not truly out of nowhere, because I noticed that I want to get ABC, the measure of ABC into the proof. I want to get equals. And this is actually what we just wrote for step 4, very, very close to this right here. Other than having 2 measure of angle 1s on the right side, I've only got 1. So how are we going to finish this? Now that everything's in the proof, what do we need to do? We need to connect previous statements. So what happened? This 2 got replaced with something that 2 was equal to. 2 is equal to 1, so I said, all right, you get right in there. I'm going to replace you with that. We should know by, again, the third or fourth time here today, that's called substitution. The substitution property of equality. We're so close. I'm always looking back there. I'm looking right here. Measure of ABC, good, equals good. Measure of angle 1 and 1, really good. The only thing we haven't done yet is tied it all together. So I know it's low on the screen here, but I'm trying to make sure I can see both. The measure of angle ABC is equal to, and we know how this is going to finish. It's always 2, it's the proof statement, measure of angle 1. How did we do that? We saw that in some of our algebra proofs. I'll do a little example up here where we saw things like 10 equals x plus x. We saw stuff like that, right? So if we were solving that algebraic equation, we would say probably the next line would be 10 equals 2x. What did we do with that? We combined like terms, we simplified it, and that's what we called it actually as far as a justification. So my last step here should be just going from step 5 to step 6 was we simplified it. We combined like terms. Remember, we said that was an option. You could call it either one. We simplified it. So I think that's definitely how we would want to finish it. That's legit. No joke. Definition of bisect or angle bisector, getting stuff into equations, that takes time, that takes practice. We've got one more to go. Let's try that blank one, okay? So that we're done there. We worked our way through it. One last time. I don't have to cover anything up because there's nothing to cover up, okay? This is our goal. This is ultimately where we want to get, where we're able to complete a proof. This is a 7-step proof. This one's kind of unique as well. Let's just focus for right now. It's kind of weird. There's 2 different proof statements. I'm going to erase this in a second, but I don't want to confuse myself. I just want to look at this first proof statement. AB is equal to 2 AM. Holy cow. Okay, so here's the picture. AB, is that true? AB is equal to 2 AMs? I don't know. Let's look at the given information. We know where to start. M is the midpoint. I'm going to try to write small because I know it's going to fill this up here. Midpoint of segment AB. So we've seen this come up already today. The midpoint, point right in the middle, divides into 2 congruent segments. That is given information. All right. And so it's kind of like the last one. We've got a sentence here. M is the midpoint of AB. We need at some point to get to an equation, an equal sign. So AB is kind of in the proof. I don't mind having it in there. We need to get at some point to an equation, though. Go from words to equation. So where do we want to go? We've got some options here. I think, let's work off this given information. What does that tell me? That tells us that if M is in the midpoint, I would typically kind of mark that as those are congruent. So I think that's kind of a logical step there to say that, based on that given information, that segment AM has to be congruent to segment MB. We weren't told that. That wasn't stated anywhere, so we actually have to state it. How did I know to mark those orange tick marks right there? Because I saw the word midpoint. The definition, DFN, of midpoint says we can do that. All right, so that's good. That gets us rolling. We've got AM is in the proof. There it is. It showed up. We want 2 of them at some point. You know what? While we're working on this right here, I think a good idea is probably just to get this. This is equals, right? This is congruence. We've got a mismatch of formats. It's always it's always the same deal. How would I go from congruence to equality? This has happened a few times today. Let's say the length of AM is equal to the length of MB. What did I do? I just straight up converted from congruence to equality using the definition of congruence. So it's a 2-way. You could go from congruence to equality or equality to congruence depending on what you want to work with. These ones almost all today have been working with equality, so that's why we switched to equality. All right, there's an AM, true AM, the way we want to see it as part of an equation. Let's go back and start working on this right here. Although we did, I guess let's work on this AB. Let's work on the AB part of it. Okay. Whoops, didn't mean to do that. Let's get AB. Right now it's segment AB. It's words, it's a sentence. I don't like that. I want to talk about AB, the actual length of AB. So what do I know about the length of AB? We kind of need to introduce this AB right here into the proof. I think a great way to introduce things for like the maybe 5th, has this come up in every proof? Maybe in all but one. That the length of AB, the big length, very generically, is equal to the length of AM, right? For sure, AM, what? Plus the length of MB. When I make that very generic statement, we introduced this AB is now in the proof. that is our segment. Just what are we working with? Angles or segments? That these are all segments. So the segment addition postulate says that has to be true. Now it's starting to look okay now. Like we could have done that. So just not make sure to avoid confusion there. Like that could have been our second step. There's not like this isn't the one only way to do this. I could have seen that right off the bat and said, you know what, let's get A, B in there. I could have done that right away for step 2, and then steps 2 and 3 would have been bumped down to 3 and 4. So that's where you get a little bit more flexibility with some of the open-ended proofs, the blank ones. But I think by step 4 now, we're starting to look like we're in pretty good shape here. I see an AB on the left. I see an equal sign. I see an AM on the right. I need 2 of them. So this is very similar to the finish on the last proof. Let's get this MB out of here and replace it with something that MB is equal to. So I'm going to say, get out of here, MB. I know MB has the same value as AM. We proved that in our third step. So now I'm ready to say that AB is equal to AM plus AM, which, how did that happen? That's our substitution property of equality. All right. We're really close right now. There's 2 AMs on the right. We do have 2 AMs on the right, just like our last proof. We want to put those together, though, and say AB equals 2 AM. So it's that same, I wrote on the last example, it's just like 10 equals x plus x. How did we go from that to 10 equals 2x? We combined some like terms. We simplified the right-hand side. Simplify. Or say combine like terms. So there we have it. Like we have checked off this proof statement. We've formally proved that using postulates, definitions, properties of equality, also properties of algebra, solving a simplify. I think this is the last one. So now I finally can look at this. All 6 of those steps were to get to that first proof statement. If I look here, there's actually a little bit of I think we're taking some liberties here. I think technically we should probably, what happened? Like AB is on the left-hand side right here, and all of a sudden the AB flip side. So this is actually a good look at like, how can I go from this, step 6, to this? I think I would technically have to do it in 2 steps. So maybe it's a good time to kind of do this one. If I just want to turn this around and say 2 AM equals AB, so all I've done from step 6 to step 7 was just flip it. That's where we would actually use that symmetric property of equality. All right, because I'm trying to make step 6 look like this, but I notice that the AMs switch sides. Okay, so that's all I've done was flip it. Now I'm still not quite here yet. There's too many AMs on the left side. I've got 2 of them. So how am I going to get rid of this 2? This is one that, depending on what your background is or how you would do this, I would probably argue that I'm multiplying both sides by 1/2. If I multiply the left side by 1/2, that cancels that 2. So it's just going to leave me with an AM there. If I multiply the right side by 1/2, it shows up as 1/2 AB. So you could also, I would totally accept if you said I divided both sides by 2, and that shows up on the right hand as 1/2. Totally fine, because multiplication, to be honest with you, and division, multiplication, property of equality, and division end up ultimately being the same operations, just one's multiplying by the inverse, by the reciprocal of a number. So that's a beast. We started that blank, and holy cow, I went through, I think, about every one of my colors except this beautiful brown right here. So, I don't know, maybe we did. No, it's orange on the last one. I used 2 oranges. So, yikes. We can do it though. Okay. So that's the lesson. That's proving statements about segments and angles. We specifically focus on there. 2.5. Make sure you're adding these and doing these with me. In your notes, just watching and hearing and seeing it isn't going to be enough. Those take practice to get good at. Okay, that's the only way we're going to get good at it, is by trying them and maybe making mistakes and correcting them. So that's the notes. Lesson 2.5 is officially done. Let's call it there. So I will see you in future lessons.